Welcome back at the second and last clip on geothermal energy storage systems. In this clip I will go into more detail on the BTES and ATES technologies, providing you also some numbers and design concepts. BTES systems consist of a set of tubes in the underground through which a medium circulates, exchanging heat with the surrounding sediments. These tubes are a couple of centimeters thick and are placed in a borehole with a diameter of about 15 centimeters. The space between the tubes and the borehole wall is filled with cement or clay to enhance heat exchange and to prevent groundwater from flowing from one layer to another. BTES systems are often referred to as closed-loop systems. When heating is needed, cold water flows into the tube, extracting heat from the surrounding soil and is then used to warm up the building. At the same time, the sediments around the borehole become cooler. During the warm periods of the year, relatively warm water is pumped through the tubes. This becomes colder and is used to cool the building. The sediments around the borehole now become warm. The diameter of the sediment volume experiencing significant thermal influence is limited, about 5 meters. We can calculate the thermal power output of a BTES systems with the equation we previously used for the geothermal systems. The temperature difference, however, is now between the in and the outflow of the pipe. The flow and the heat capacity refer to the medium inside the pipe. Because of energy conservation law, the amount of heat extracted by the medium circulating inside the pipe must be equal to the heat flowing towards the borehole. This heat flow is calculated with the heat conduction equation. This says that the heat flow is determined by the total area of the tube over which heat conduction occurs, the temperature difference between inside and outside the pipe, and the thermal conductivity of the materials, kappa. You should note that because of the temperature of the medium in the pipe changes, the heat flow can only be calculated for single pipe segments where the conditions are constant. By adding all these heat flow of these segments, we can obtain the total heat flow to the borehole. Typical heat flow rates for BTES systems are 20 to 80 watts per meter borehole length, depending on the type of heat exchanger, the soil and medium temperatures, and the type of soil, of course. This means that a single family house, typically requiring a heating and cooling capacity of a couple of kilowatts, will need a borehole length of about 50 to 300 meters. This can be one single borehole if local geology allows this, but may also be multiple boreholes if the sediments are not thick enough. Let us now focus on ATES. The transport mechanism here is convection, which means that we use groundwater as a medium to transport the heat to or from the aquifer depending on the season. Unlike with BTES systems, where the soil around each borehole is warmed up and cooled down over the season, with ATES we store the warm and the cold water at different locations. This enables larger temperature differences and thus higher capacities. The wells used in ATES systems are pipes with a perforated screen across which water is pumped radially to or from the well depending on the pump direction. In the slides, we assume that the aquifer has an ambient temperature of 12 degrees. When heating is required, the warm water previously stored in the aquifer is extracted to heat the building. The groundwater then becomes colder and is pumped back into the aquifer, thereby cooling down a volume of sediments around the cold well. Obviously, at the same time, the volume of the warm sediments around the warm wells shrink. During cooling demand, the flow direction is reversed. Cold water, which was stored in the aquifer, is now used to cool the building, becomes warmer and is then stored again in the aquifer for the next heating season. The radius of the volume affected by temperature change is about 50 to 150 meters and depends on the aquifer thickness and storage volume required to provide the heating or cooling. The distance between the wells must be large enough to prevent negative interaction between warm and cold zones. As a result of the radial flow around the wells, the heat stored in the aquifer will form a cylindrical volume around the well itself. The size and the shape of the cylindrical body play an important role in designing ATES systems. The warm or cold water stored in the aquifer will exchange heat via conduction with the surrounding sediments, thereby decreasing the efficiency of the system. Because these exchanges occur at the boundary of the cylinder, the total surface area of the cylinder must be as small as possible to optimize performance. The surface area of this thermal cylinder is determined by the cap and the bottom, where losses occur to the confining layers, and the circumference, where losses occur to the surrounding aquifer. The smaller this total area is relative to the stored volume, the more efficient the system is. We know that there is a negative linear correlation between the efficiency of ATES systems and the area over volume ratio. Therefore, we design ATES systems to minimize this ratio. The value of the A over V ratio depends on the required storage volume, controlling the diameter of the cylinder, and on the screen length of the perforated screen. Obviously, this length will be equal or smaller than the thickness of the aquifer. If large storage volumes of water are needed, for instance 250,000 cubic meters, we will need to find aquifers which are at least thicker than about 50 meters. As you can see in the graph, at thinner aquifers, the A over V values strongly increase and the ATES systems will be inefficient. Similar results is obtained for even larger volumes of 1 million cubic meters. If smaller volumes are needed, for smaller buildings, the A over V ratio is much larger, but thinner aquifers can be targeted. For the case of 10,000 cubic meters, a 20 to 30 meter thick aquifer will provide the highest efficiency. Identifying the aquifer thickness is therefore a key step in designing ATES systems. In practice, we cannot freely choose the well screen length, as aquifer thickness varies depending on local geologic conditions. You can use this relation between aquifer thickness and losses to identify the most suitable aquifer for any required storage volume. Remember that the examples provided here refer to simple situations where, for instance, no regional groundwater flow or density difference due to high storage temperatures occur. We now come to the end of the last clip on heat storage and recovery in the shallow subsurface. At present, there are about 3,000 ATES systems operational in the world, and this number is rapidly increasing. BTES systems are already more established. The exact numbers are not known, but estimates run up to 1 million worldwide already. This difference is not strange, as BTES can be applied at any type of underground and also as there are many more suitable small buildings. Recent studies indicated that ATES and BTES systems combined can potentially cover about 10% of all current heating and cooling demand worldwide. This means that the number of systems that will be installed the coming decades will grow considerably. We can now use your experience to design, build and operate them. We hope you enjoyed this MOOC and hope to see you again at another MOOC or as a student or a colleague at the TU Delft campus, where many of the buildings are heated and cooled with geothermal energy.